Today we're going to work on section 3.6, which is all about practicing the sketching of graphs and functions. So the first one, we're going to work on this function right here, x to the fourth plus 4x cubed, and kind of walk you through all the things that we know about functions, derivatives, second derivatives, intercept points, x and y intercepts, and see if we can't come up with enough information that we could sketch a very accurate graph or picture of this function. So first thing I would start with is just looking at the domain. Are there any x values that I cannot use that would be resulting in either a whole discontinuity or an asymptotic behavior where I'd have an asymptote? And since this is a polynomial, polynomials, we all know, behave quite nicely, and that would mean that I would conclude the domain would be all real numbers. So any x I want to put in, I certainly can. Asymptotes, well then I'm expecting no asymptotes whatsoever, since every domain value looks pretty good. And where do I want to go from there? I could think about x and y intercepts. Those are concepts that we learned in advanced algebra and even probably before. An x-intercept is where it intercepts the x-axis, right? And that means that the y value would be 0. So if I put in a y value of 0, I would find my x-intercepts. So if I set this equal to 0, and here I'm working on x-intercepts if you want to label your region, I could factor this thing, pull out an x cubed, and I would have x plus 4, and then the regions, or the 2 points that this occurs, would be x equals 0 and x equals -4. So I would have two x-intercepts. I would have when x is 0, I get out 0. And then I'd also have when x is -4, I get out 0. Y-intercepts, well, that's talking about where does it intercept the y-axis, and that occurs when x is 0. So I could find my y-intercept by plugging in 0 into the function. So y is equal to 0 to the fourth plus 4 times 0 raised to the third. But that means that y is equal to 0. So when x is 0, y is 0. And look at there that we already had that point identified, 0, 0. So far I know a couple very key points to my graph, and that can help my accuracy because I could plot those out. I'm going to have intercepts at 0, 4, -4, 0, and then a repeat there at 0, 0. Okay, I could answer questions about increasing and decreasing functions if I looked at part A, the first derivative. So let's take our first derivative, f prime of x would equal 4x cubed plus 12x squared. And I want to find my critical points from this so I can tell where it's increasing and decreasing. So 0 is equal to 4x squared, I'm factoring at the same moment here, times x plus 3. Double check our work, that gives us 4x cubed plus 12x squared. This occurs when x is either 0 or -3. So I have two critical points. Take it into a sign graph, or sign chart. I have one at 0 and I have one at -3. In those regions, let's check out our work. Maybe we'll plug in -4 back into the first derivative. If I put in -4 into my first derivative here, I would have a positive value followed by a negative value. This will be negative. In the region between -3 and 1, let's select -1. When I put in -1, I'd have a positive amount because I square it, And -1 plus 3 would be a positive amount. So this ends up being a region that is positive or increasing. Let's select 1. When I take 1 and square it, it's going to be positive. And then I take 1 and add 3 to it, it's still positive. So I get a region of positive here. So I would have decreasing function followed by increasing. So over on this, I could write this as 4x cubed plus 12x squared. Intervals where it's increasing. Looks like it's from -3 to infinity. Because that's the regions where I had positive followed by positive. Intervals where it's decreasing, I would say from -infinity up to -3. Oh, I see I have a sign chart up there. Next, let's go into second derivative. Second derivative would be 12x squared plus 36x. I'm sorry, 24x. 2 times 12 would give me 24x. Now, from the second derivative, I can pick up points of inflection, possible points of inflection. So, y double prime equals 12x squared plus 24x. This is going to give me information about concavity. So let's set this equal to 0, and I would have 24x plus, I'm sorry, I'm taking third derivative. Let's pull out the 12x, and that's going to give me x plus 2. I have 2 key locations here, 0 and -2 is where the second derivative is equal to 0. Second derivative does not exist, results in no possible points from that scenario. So my 2 points that I'm interested in are 0 and -2, and I would plot those out on a second derivative sign chart. And now I just got to test some regions. So let's test in this left area of -2. Putting in -3, I would have a negative from that. And then I would have also another negative when I put -3 plus 2 would result in negative. Negative gives me positive. In other words, this is concave up. When I put in -1, I would have a negative followed by a positive. That's a negative region, it's going to be concave down. When I put in +1, I would have a positive, 12 times 1 is positive, and then 1 plus 2 is positive because that's +3, and that's going to be concave up. So, concavity here. Intervals where it's concave up, I would have -infinity to -2. Also, I would have 0 to infinity. I'm reading this strictly from my sign chart here. Positive and positive, concave up, concave up. Intervals where it's concave down would be that middle ground between -2 and 0. Do I have any relative maxes or mins? Wish I still had my first derivative sign chart up, so I'm going to repeat that. We had points of interest at -3 and 0, if I'm not mistaken, and it was increasing from -3 to infinity and decreasing there. So this went down and back up. I had a min at -3. So we had a relative min at -3 comma something, and there is no relative max because it continues to go up, up, up. So none there. Inflection points, we had an inflection point at -2 comma something and also at 0 comma something. Well, when I put in 0 into my original function, I get out 0. And if I put 2 into my original function, you get negative 16. Just go back up to the top of the page and put it into f of x equals x to the fourth plus 4x cubed, and you will come up with the fact that it's negative 16. I've already done the work for negative 3. When I plugged negative 3 in f original, I got out negative 27. So f of negative 3 gave me negative 27. Now, there's a lot of information here that we can use to sketch a graph. And I'm going to combine my sign chart all together here. So that's going to give me kind of one very interesting sign chart. We had critical point at negative 3, we had an inflection point at negative 2, and then 0 crept up for both critical point as well as a point of inflection. So I know that this one is a relative min though, and these are going to be points of inflection because this was not a relative max at 0. My first derivative test and my second derivative test can kind of be combined here. And the first derivative test went negative, and then it was followed by positive regions. From negative 3 to infinity, it was increasing. My second derivative test went positive, positive, and then after negative 2, after negative 2 went, oh, this went back positive there. So the only region I had negative for second derivative was between negative 2 and 0, and that's what this is saying. So now, what I'm going to try and do is just think about if I have a decreasing function that is concave up, it would look something like this. Decreasing manner, concave up. When I have increasing function with concave up, it would look like this. So I now kind of have a notion of what this function's doing. It reaches this minimum right here, doesn't it? Then I've got to follow up by an increasing function that's concave down. Increasing concave down is going to have the overall general shape of that. And then increasing concave up is going to do this number. So, you know, if you can think of those greens kind of connecting together, it gives us the general shape of our function. Let's try to do some sketching. So, create a nice coordinate plane for yourself. Some of the key figures I'm going to have on are at negative 4, and then I'm going to put in negative 2, 0, 2, 4. I'll go ahead and put 1 and 3 in here as well. Might as well put negative 1, negative 3, what the heck. Okay, all our information, 0, 0, that is a hard point. Negative 4, 0 was an x-intercept, and 0, 0 was a y-intercept. We had a relative min at negative 27. Okay, now I'm going to extend this page, take this down a little ways. I'm going to count by tens. So negative 10, negative 20, negative 30, and up above, I'll go in positive 10. So, looking back at our sheet, you guys have the advantage, you've got it all right in front of you. Negative 3, negative 27 was a relative min. Negative 3, negative 27, a relative min. And I remember that this thing was concave up, but decreasing. Then it went back to concave up, and I have a point of inflection at negative 2. But I have that point identified as negative 2, 16. So negative 2, 16, it's going to be concave up increasing. But at negative 2, we switch over to a concave down between negative 2 and 0. So I have to switch my concavity, and that makes sense because I've got to come through 0. But 0 isn't a max, so I don't want to keep curving down. And in fact, looking back at our combined sign chart, at 0, we switch to concave up increasing. So not only my function is increasing and it continues to increase, but not with a concave down. It switches over to concave up and must continue on its way like that. And there we have a nice curve sketch using lots and lots of ideas, intercepts, minimums, maximums, points of inflections, concavity, and it all rolls together nicely. You may try to do your best at 4 problems, and let me grab those. These 4 problems found on page 215 will give you some experience sketching by hand the curves, and of course you can throw them in your graphing calculator and verify that you did a nice job. So good luck with this.